Can you imagine doing physics without calculus? No, me neither. What calculus is to Newtonian mechanics, quantum field theory is to the standard model. Quantum field theory provides the fundamentals on which the standard model, the theory of fundamental particles, is built. It is a necessary relativistic extension of quantum mechanics and much more than that. Quantum field theory describes everything to quantum fields. Like classical fields, these fields have a quantity at every point in space. In contrast to classical fields though, they are quantized. In quantum field theory, elementary particles are the outcome of excitations of these quantum fields. The fields explain why all particles of the same type are indistinguishable. In quantum mechanics, particle number is conserved. From many experimental facts, such as the decay of muons, we know that in fact particles can be created and destroyed. In a quantum field theory, particle number is not necessarily conserved. This allows particles to be produced and annihilated. In high-energy physics experiments, two beams of relativistic particles are collided to produce new particles. The new particles are not observed directly, but by their decay products. In general, we're interested in calculating scattering cross-sections and decay rates. A direct calculation can be cumbersome. Luckily, there's a powerful tool called Feynman diagrams with corresponding rules to do these calculations easily. We can take as an example the muon production through electron-positron annihilation. This process was studied in lepton colliders around the world. In order to calculate its cross-section, we should write down all Feynman diagrams for this process. If we use, as an approximation, only leading order, there are just two diagrams. One with an intermediate photon and one with an intermediate C boson. The Feynman rules give vectors that enter the cross-section for each line and vertex. Let's write down the expressions for both diagrams. This is the diagram with the C boson propagator. Let's start by denoting down the momenta. We use P1 and P2 for the incoming momenta, Q for the momentum of the C boson, and P3 and P4 for the outgoing momenta. The next step is to write down spinors for all the particles. For the incoming positron, we write down the U spinor. And since it is an antiparticle, we use a bar. Every spinor is also dependent on its momentum. That's why we write it down between the brackets. Next, we write down the vertex with the Z boson. This is the expression for the vertex with the Z boson. Then we write down the spinor for the incoming electron. Since this is also an incoming particle, we use another U spinor. Next, we write down the propagator for the Z boson. This is a propagator for a massive particle. The next step is to write down spinors for the outgoing particles. These are two muons, a mu plus and a mu minus. First, we write down the spinor for the outgoing mu minus. Since this is an outgoing particle, we use a V spinor. Again, we use a C boson vertex. And finally, we write down the spinor for the outgoing mu plus. This is the diagram for the photon propagator. The procedure of writing down its expression is similar to the previous diagram. The vertices now have the coupling constants of the photon. The propagator changes because the photon is massless and the C boson was not. The incoming and outgoing spinors remain the same. That the Z-boson propagator enters the cross-section can be seen from these measurements of the Aleph experiment at the Large Electron-Positron Collider. The expression for the propagator gives rise to a characteristic shape called Bright-Wigner distribution. This can be fitted directly to the cross-section as a function of energy. The agreement is spectacular. Field theory has become an essential tool for models in high-energy and solid-state physics. In its ability to make predictions for experiments, it goes unmatched. However, it is not the end of the story yet. The electromagnetic, weak, and strong force are successfully described in a unified quantum field theory, but gravity is described by general relativity. For a long time, physicists have been thirsty for a theory of everything that can explain four fundamental interactions of nature in a unified framework. We have seen what a quantum field theory of three forces is and how it's able to describe experiments. We can only imagine what a true theory of everything can do.